The nearest star to Earth, outside our own Sun, is a red dwarf called Proxima Centauri. It sits at a distance of 4.24 light-years, roughly 40 trillion kilometers, or 25 trillion miles. These numbers are large, but they have been recited so often in popular science, but they have acquired a kind of comfortable familiarity. The way large national debts or population figures become familiar through repetition without ever quite becoming real. So let us make it real, just once, before we begin. The Voyager 1 spacecraft, the fastest moving object ever launched by humanity, on a sustained outward trajectory, travelling at approximately 17 kilometers per second, a speed that would carry it from New York to Los Angeles in 4 minutes, has been travelling since 1977. It has been travelling for nearly 50 years. It is roughly 23 billion kilometers from Earth, and Proxima Centauri is 40 trillion kilometers away. Voyager 1, at its current speed, would reach Proxima Centauri in approximately 73,000 years. Not 73 years, 73,000. And Proxima Centauri is the closest star. It is not a destination we chose for its interest or its promise. It is the nearest possible target, the lowest possible ambition of interstellar travel, and at the fastest speed humanity has ever achieved with a real spacecraft, it is 73,000 years away. We have not yet built the first brick of civilization that would be standing when Voyager arrived, if Voyager were aimed at Proxima Centauri, which it is not. If you enjoy videos that look directly at the hardest problems in space science, that refuse to soften the numbers or paper over the difficulties with optimism that the physics does not support, I genuinely appreciate it if you hit that like button and subscribe. It helps more than you know. Now, settle in, get yourself nice and comfortable. Let's begin. The most common misconception about interstellar travel is that it is a problem of technology, that we simply need better rockets, more advanced engineering, a few more generations of research and development, and the stars will open up to us, the way the Americas opened up to Europeans once ship design improved. This framing is wrong, in a way that is not merely a matter of degree, but of kind. The obstacles between us and the nearest star are not primarily technological in the sense of we haven't figured out the engineering yet. Several of them are consequences of the laws of physics as we currently understand them. Laws so well tested, so precisely confirmed, so deeply embedded in the structure of reality that the probability of them being wrong in any way that helps us is negligibly small. The rocket equation is not a temporary limitation, awaiting a clever solution. The finite speed of light is not a speed bump that future engineering will smooth out. The energy required to accelerate a spacecraft to meaningful fractions of the speed of light is not a cost that clever design can dramatically reduce. These are the bedrock constraints of the universe, and the question of whether we will ever reach another star is in large part a question of whether any plausible physical mechanism exists that navigates around them. The honest answer, examined carefully, is we do not know, and the reasons for doubt are serious and deep. This video is an examination of those reasons. Begin with the most fundamental obstacle, distance, and what it demands. The distance to Proxima Centauri, 4.24 light-years, is, in everyday terms, completely inconceivable. We do not have a reliable intuition for it, but let us try to build one. Miss 551,554. If the Earth were a grain of salt, 1 millimeter across, and you placed it on a table, the Sun would be a sphere, roughly 11 centimeters in diameter, about the size of a grapefruit, sitting about 12 meters away from the grain of salt, on the other side of a large room. In this scale model, where the Earth is a grain of salt and the Sun is a grapefruit 12 meters away, Proxima Centauri would be another grapefruit sitting approximately 3,200 kilometers away. Not across the room, not across the building, not across the city, across a continent. If the Sun is a grapefruit in New York, Proxima Centauri is a grapefruit somewhere near Los Angeles, not in the sense that the distance is comparable to a transcontinental flight, but in the literal sense that in this scale model, the two nearest stars to each other are separated by the width of a continent. The space between stars is not vast in the way that the ocean is vast, or even in the way that the solar system is vast. It is vast in a way that requires a different category of description entirely. Proxima Centauri is part of the Alpha Centauri system, a triple star system that is, as a whole, the closest stellar system to ours. Alpha Centauri A and Alpha Centauri B are a binary pair, two stars orbiting each other with a period of roughly 80 years, separated on average by about 23 astronomical units, comparable to the distance between the Sun and Uranus. Alpha Centauri A is a star very similar to our Sun, slightly larger and slightly more luminous, a G-type main sequence star that has been burning hydrogen for approximately 6 billion years, older than our own Sun, which is 4.6 billion years old. Alpha Centauri B is slightly smaller and cooler, an orange dwarf. Both are, in principle, capable of harboring planetary systems. Neither has confirmed planets as of this writing, though the radial velocity searches have been difficult because the orbital motion of the two stars around each other creates a complex signal that makes planet detection challenging. Proxima Centauri, the third member of the system, orbits the central pair at a distance of roughly 13,000 astronomical units, so far that its orbital period around Alpha Centauri A and B is estimated at roughly 500,000 years. It may be only loosely gravitationally bound, and some calculations suggest it may not complete a single orbit before being stripped away by galactic tidal forces. Proxima is a red dwarf, a class Meters star with roughly 12% of the Sun's mass, about 14% of the Sun's diameter, and a luminosity of only about 0.15% of the Sun's. It is far too dim to be seen with the naked eye from Earth, despite being our closest stellar neighbour. It sits at magnitude 11.1, invisible without a telescope. The Alpha Centauri system as a whole sits at approximately 4.37 light-years from Earth. Proxima, orbiting far from the binary pair, is slightly closer at 4.24 light-years, hence its distinction as the nearest individual star. The distance between our Sun and Alpha Centauri A is roughly the same as the distance between Proxima and Alpha Centauri A, within the uncertainty of current measurements. Beyond Alpha Centauri, the nearest stellar neighbourhood within 10 light-years contains a modest but interesting collection of stars. Barnard's star, a red dwarf at 5.96 light-years, is the second closest stellar system and the fastest moving star in the sky. It has such a large proper motion relative to Earth, but it shifts its position on the sky by more than half a degree per century, a rate large enough that if you photographed it through the same telescope every 10 years, the shift would be easily visible. Dwarf 359, a dim red dwarf at 7.78 light-years, is familiar to science fiction audiences as the site of a famous battle in Star Trek. Sirius, the brightest star in the night sky, is 8.6 light-years away and is itself a binary, a brilliant white A-type star orbited by a white dwarf, the burned-out remnant of a more massive companion star that exhausted its fuel billions of years ago. Epsilon Eridani, a relatively young orange dwarf at 10.5 light-years, has a debris disk and possible planetary system, and has been a perennial target for SETI observations for decades. Ceti, a Sun-like star at 11.9 light-years, has a planetary system with at least 4 confirmed planets, though they orbit in a debris disk so dense with cometary material that bombardment rates may be too high for surface life to persist. This is the neighbourhood. Within 12 light-years of the Sun, there are roughly 30 star systems containing about 40 individual stars. Most are red dwarfs, dim, long-lived, variable in activity. A few are Sun-like. None have confirmed habitable zone rocky planets with atmospheres known to be friendly to life, though the survey is incomplete. This is the full list of destinations that fall within the range of the most optimistic near-term interstellar proposals, within the zone where Breakthrough Starshot Flyby Probe or a Daedalus-class fusion probe might arrive within a human lifetime, or a few human generations. Now, introduce the speed limit. The speed of light, 299,792 kilometers per second, is not merely the fastest speed humans have achieved, or even the fastest speed currently achievable with known technology. It is, as best we can determine, the absolute maximum speed at which any physical object can travel through space. It is built into the structure of space-time in a way that has been tested to extraordinary precision and that no credible physical theory challenges. And light itself, travelling at this maximum speed, takes 4.24 years to reach Proxima Centauri. 4 years and 3 months. For any spacecraft slower than light, the journey is longer. For any spacecraft at realistic speeds, say 1% of the speed of light, which would be 1,000 times faster than Voyager, the journey takes 424 years. 4 centuries. For 10% of the speed of light, which represents the upper bound of what fusion-powered propulsion might theoretically achieve, the journey takes 42 years. 44 years, 42. For 1/10 of the speed of light, still 20 times faster than anything we have ever built, the journey takes 4,240 years. These are just the travel times. They say nothing about the energy required, the shielding needed, the life support systems, the communication infrastructure, the deceleration at the destination, or the thousands of other engineering challenges that would need to be solved for any of these journeys to be real rather than hypothetical. They are the absolute minimum time floor, set purely by the speed of the vehicle. And already, for every realistic vehicle we can conceive of with current or near-future technology, the floor is centuries. This is the situation. This is what we are actually discussing when we discuss interstellar travel, not a hard engineering challenge with a clear path to solution, but a confrontation with physical reality that may have no solution compatible with human civilization as it currently exists, or as it can plausibly exist. Let us now go through the specific obstacles in detail, because each one is worth understanding deeply, and because the combination of them, the fact that they stack, that solving one does not solve the others, is what makes the problem so severe. The first obstacle is the rocket equation, and it deserves more attention than it typically receives in popular discussions of interstellar travel. The Tsiolkovsky rocket equation, derived in 1903 by the Russian mathematician Konstantin Tsiolkovsky and confirmed countless times in a century since, describes the relationship between the final velocity of a rocket, the velocity at which it expels its propellant, and the ratio of the initial mass to the final mass. In its simplest form, it states delta V equals V exhaust times the natural logarithm of the mass ratio. Delta V is the change in velocity the rocket achieves. V exhaust is the velocity at which propellant is expelled from the engine, a measure of how energetically the propellant is ejected. Mass ratio is the ratio of the initial mass, mostly propellant, to the final mass, which is the payload plus the empty rocket structure. The natural logarithm is the killer. The logarithm grows slowly. To double the delta V, you do not double the mass ratio. You must square it. To triple the delta V, you must cube the mass ratio. To achieve delta V equal to 10 times the exhaust velocity, the mass ratio must be e to the power of 10, approximately 22,000 to 22,000 kilograms of propellant for every kilogram of payload. And this is for a single stage, for a rocket that burns all its propellant in one continuous burn. Multi-stage rockets help, but each stage must carry the mass of all the stages above it, and the exponential character of the problem does not go away. Now apply this to interstellar travel. The best chemical rockets, burning hydrogen and oxygen, achieve exhaust velocities of about 4.4 kilometers per second. The speed needed to reach Proxima Centauri in a human lifetime, say, 10% of the speed of light, or 30,000 kilometers per second, is merely 7,000 times this exhaust velocity. The mass ratio required is e to the power of 7,000, a number so large that it has no name, a number so large that if every atom in the observable universe were a kilogram of propellant, it would not remotely suffice. Chemical propulsion is not a starting point for interstellar travel. It is categorically excluded by the mathematics. Nuclear propulsion helps. A nuclear thermal rocket, heating hydrogen propellant in a nuclear reactor, achieves exhaust velocities roughly twice those of chemical rockets, about 8 to 10 kilometers per second. Better, but the improvement is incremental rather than transformational. The mass ratio for 10% of the speed of light is e to 3,000, still astronomical. Nuclear pulse propulsion, the Project Orion concept in which nuclear bombs explode behind the spacecraft, can achieve exhaust velocities of thousands of kilometers per second. At an exhaust velocity of 3,000 kilometers per second, the mass ratio for 10% of the speed of light is e to the power of 10, approximately 22,000. This is actually manageable. It is a large number, but it is a number that exists within the realm of conceivable engineering, not beyond the number of atoms in the universe. An Orion-type spacecraft could, in principle, achieve a few percent of the speed of light with a mass ratio of a few thousand, given sufficient nuclear material. Project Orion was not a theoretical exercise. It was a serious, funded, government-supported engineering program. From 1958 to 1965, under the auspices of General Atomics and the Advanced Research Projects Agency, the predecessor to DARPA, a team of physicists and engineers, including Ted Taylor, one of the most creative nuclear weapons designers of his era, and Freeman Dyson, the legendary mathematician and physicist, worked out the detailed engineering of a spacecraft driven by nuclear explosions. Taylor's contribution was the design of extremely efficient, very small nuclear devices, shaped charges optimized for maximum impulse by unit of nuclear material that could be mass-produced at reasonable cost. Dyson's contribution was the theoretical framework and the breathtaking ambition. He envisioned Orion not as a small probe, but as a true interplanetary and eventually interstellar vehicle, capable of carrying hundreds of people to other planets in the solar system and, in its largest incarnations, potentially to other stars. The small-scale proof of concept, a roughly 3-meter diameter model given by conventional chemical explosives rather than nuclear charges, called the Hot Rod, was built and flown in 1959. It worked. The pusher plate, shock absorbers, and basic flight dynamics were validated. The concept was physically sound. The path from the hot rod to a nuclear-powered vehicle was straightforward in principle, requiring nothing more than replacing chemical explosives with nuclear charges and scaling up the structure. The engineers were confident. Dyson was exhilarated. The project's classified status limited external scrutiny, but internal assessments consistently found no fundamental physical obstacles. What killed Orion was the 1963 Partial Nuclear Test Ban Treaty, which prohibited nuclear weapons tests in the atmosphere, in outer space, and underwater. A nuclear pulse spacecraft operating beyond Earth's atmosphere would, in the process of firing its drive, detonate hundreds or thousands of nuclear devices in space, precisely what the treaty prohibited. The political and strategic context of 1963, with the United States and Soviet Union locked in tense nuclear standoff, made any exception to the test ban politically impossible. Orion was quietly shelved. Dyson, writing about the episode years later, described it as one of the great might-have-beens of the space age, a technology that could have opened the solar system and perhaps eventually the stars, surrendered to the understandable but ultimately counterproductive caution of the arms control era. The physics of Orion was never refuted. The engineering was never shown to be impossible. The concept was abandoned for political and legal reasons, not scientific ones. A civilization that chose to revisit nuclear pulse propulsion with modern nuclear engineering, modern materials science, modern computational design tools could almost certainly improve substantially on the 1960s designs. Combined with advances in nuclear devices, shock absorption, and spacecraft structure, a modern Orion-class vehicle might achieve exhaust velocities significantly higher than the original estimates. Whether this translates to practically achievable interstellar velocities depends on the specifics, but the baseline physics has never been in doubt. The challenge is always the sheer scale of what interstellar travel requires, even with the best available rocket technology. An Orion-class vehicle, achieving 3% of the speed of light, would reach Proxima Centauri in roughly 140 years, the better part of 2 centuries. A vehicle achieving 10% of the speed of light, requiring exhaust velocities and mass ratios significantly beyond the original Orion estimates, would reach Proxima in 42 years. Both are within the range of physics. Neither is within the range of current civilization's will, resources, or political consensus. And both face the same deceleration problem. The propulsion required to stop at Proxima Centauri is as large as the propulsion required to get there, compounding the fuel requirements ferociously. The second great obstacle is energy, and it connects directly to the rocket equation, but extends beyond it. Even for non-rocket propulsion concepts, systems that do not carry their own fuel, the energy required to accelerate a spacecraft to significant fractions of the speed of light is staggering by any measure of current human energy production. Consider a 1-ton spacecraft, about the mass of a small car, accelerated to 10% of the speed of light. The kinetic energy of this spacecraft, calculated relativistically, is approximately 4.5 times 10 squared 0 joules. To put this in human terms, total global energy consumption in the year 2023 was approximately 6 times 10 squared 0 joules. So the kinetic energy of a 1-ton probe at 10% of light speed equals roughly 3/4 of all the energy consumed by all of humanity in an entire year. All the electricity, all the fuel, all the heat, all the transportation, all the industrial processes, all of it, summed over 365 days. A crewed spacecraft would need to be considerably more massive, hundreds or thousands of tons, for life support, fuel, shielding, communication systems, scientific instruments, deceleration propellant. Scale the mass up 1,000-fold to a spacecraft massive enough to carry a crew, and the energy requirement scales proportionally, 1,000 years of current global energy consumption, to accelerate the spacecraft 10% of the speed of light. And 10% of the speed of light means a 42-year journey to Proxima Centauri, one way. Most serious proposals for human interstellar travel aim for much lower speeds. At 1% of the speed of light, which reduces the energy requirement by a factor of 100, the journey time is 424 years. Still prohibitive for a human crew without multi-generational planning. To make the journey in a human lifetime, at constant acceleration, you need to reach a significant fraction of the speed of light, which requires even more energy. There is no comfortable middle ground, where the energy is manageable and the journey time is human scale. The two requirements pour in opposite directions, and physics enforces the tension between them without compromise. Where does this energy come from? No existing terrestrial energy source comes close to the requirements. Nuclear fission, the energy source of nuclear weapons and nuclear power plants, has an energy density of roughly 8 times 10,113 joules per kilogram of fuel. To provide the kinetic energy of our 1-ton probe at 10% of the speed of light, you would need about 5,600 tons of fissile material, uranium or plutonium, for a crewed spacecraft at the same speed, millions of tons. Nuclear fusion, the energy source of hydrogen bombs, not yet achieved in a controlled, sustained form in any power plant, has an energy density of roughly 3.4 times 10⁻114 joules per kilogram, about 4 times better than fission, still requiring hundreds of thousands of tons of fuel for a crewed mission. Antimatter annihilation is the theoretical maximum, 9 times 10 joules per kilogram, representing complete conversion of mass to energy. With antimatter fuel, the energy requirements become manageable. A crewed ship could be fueled with a few tons of antimatter rather than millions of tons of fusion fuel. But producing antimatter in the quantities needed, tons of antihydrogen, is so far beyond current capabilities that it belongs to a different era of civilization entirely. The total production of antihydrogen by human civilization to date, through all the particle physics experiments ever conducted, amounts to perhaps a few nanograms. Scaling from nanograms to tons is a factor of roughly 10 to the power of 12. A trillion. Even assuming that the efficiency of antimatter production improves dramatically with technological development, the gap between where we are and where we need to be is not a gap that closes in decades or even centuries. It is a gap that might close in millennia, or might not close at all if there are physical limits on antimatter production efficiency that we have not yet encountered. The third obstacle, often underappreciated in popular discussions, is deceleration. A spacecraft travelling at 10% of the speed of light must not only be accelerated to that speed, it must also be decelerated at the destination, if the goal is to stop there rather than fly through. Deceleration requires the same energy as acceleration, and it must be achieved at Proxima Centauri, where there is no pre-existing infrastructure, no fuel depot, no ground crew. The spacecraft must carry its deceleration propellant, or use some other mechanism, to brake from 10% of light speed to rest, and the mass of the deceleration propellant must itself be accelerated from Earth. In a traditional rocket architecture, the deceleration propellant must be included in the initial mess, and its mass is subject to the same rocket equation as the rest of the propellant. The combined effect is that the mass ratio for a journey that both accelerates to 10% of light speed and decelerates to rest at the destination is roughly the square of the mass ratio for acceleration alone. If acceleration to 10% of light speed required a mass ratio of 22,000, the round-trip mass ratio, accelerate, coast, decelerate, re-accelerate for return, coast, decelerate at home, is approximately 22,000 to the fourth power. A number that once again exceeds the number of atoms in the known universe. This is why the proposals for near-term interstellar missions, such as Breakthrough Starshot, focus exclusively on flyby missions for tiny, ground-scale probes. No deceleration. Accelerate to a significant fraction of the speed of light using a powerful ground-based laser, coast to the target star, fly through the system gathering what data can be collected in seconds of closest approach, and transmit the data back. No mass ratio problem at the destination, because there is no deceleration. The probe arrives, passes through, and continues into interstellar space. This is the only approach that makes the energy and mass requirements even remotely manageable with conceivable near-future technology. And even this approach faces severe challenges, which we will discuss in detail. The fourth obstacle is radiation, and it operates on two distinct fronts. The first is the radiation environment of interstellar space itself. The galaxy is permeated by cosmic rays, high-energy particles, mostly protons and atomic nuclei, travelling at near-light speed, produced by supernova explosions and other energetic astrophysical events. These cosmic rays would penetrate any but the most massive shielding and, over a journey of decades or centuries, would deliver a cumulative radiation dose sufficient to cause serious genetic damage to unshielded biological material. The radiation environment in interstellar space is significantly harsher than in low Earth orbit, where astronauts on the International Space Station receive radiation doses roughly 10 times higher than on the ground, and significantly harsher even than in deep space beyond Earth's magnetic field, where Apollo astronauts experience radiation that would, over years or decades, significantly increase cancer risk. To quantify this more precisely, an astronaut in low Earth orbit receives approximately 150 to 200 millisieverts of radiation per year, roughly equivalent to 500 to 700 chest X-rays. Astronauts on the International Space Station, during a 6-month mission, absorb about 100 millisieverts total. The annual radiation limit for occupationally exposed workers in most countries is 50 millisieverts per year. Long-duration spaceflight in low Earth orbit already pushes astronauts toward or past lifetime career radiation limits. In deep interstellar space, beyond the heliosphere, the magnetic bubble created by the sun's solar wind that partially shields the inner solar system from galactic cosmic rays, the dose rate is estimated at roughly 400 to 900 millisieverts per year. This is 4 to 9 times the occupational annual limit. Over a 40-year journey to Proxima Centauri, at 10% of the speed of light, an unshielded crew would receive approximately 16,000 to 36,000 millisieverts, 10 to 20 times the dose that causes acute radiation syndrome, 100 times the dose that is considered a lifetime career limit for radiation workers. The radiation dose during a mass mission to Mars, which would take roughly 6 to 9 months each way through deep space, is estimated at around 300 millisieverts for the transit alone. According to measurements made by the Curiosity rover's radiation assessment detector during its journey to Mars. This is already a significant fraction of NASA's career radiation limit for astronauts. An interstellar mission would face this rate continuously for decades, not months. The shielding required to reduce the galactic cosmic ray dose to manageable levels, roughly 1,000 grams per square centimetre of water-equivalent shielding, is estimated as sufficient to reduce the dose rate by about 30%, translates to hundreds of tons of shielding material for a spacecraft of human habitable size. This shielding mass compounds the propulsion problem severely because it must be accelerated along with everything else. The second radiation front is the one the spacecraft creates for itself by travelling fast. At 10% of the speed of light, the interstellar hydrogen atoms in the spacecraft's path are encountered as a stream of energetic particles approaching at 10% of light speed. In the spacecraft's reference frame, these hydrogen atoms have kinetic energies of roughly 4.7 million electron volts each, comparable to the energies of particles produced by early particle accelerators. Each hydrogen atom is in effect a cosmic ray particle generated by the spacecraft's own motion. The interstellar medium, at 10% of the speed of light, irradiates the spacecraft's forward face with a continuous particle flux. The faster the spacecraft, the more energetic and more numerous the particles encountered per second, because the ship is sweeping through more volume of interstellar medium per unit time as speed increases. At 20% of light speed, the flux and energy quadruple. At 50%, the energies become genuinely destructive, equivalent to a continuous high-energy particle beam hitting the spacecraft from directly ahead. Protecting against this requires either an enormous physical shield of material ahead of the spacecraft, meters of hydrogen ice or other ablative material that erodes slowly over the journey, absorbing the energy of incoming particles before they reach the sensitive structures behind, or an electromagnetic deflection system that ionizes and deflects incoming charged particles before they reach the spacecraft. Both add mass, complexity, and failure modes. The electromagnetic deflection approach requires continuous power throughout the journey and must maintain a field strong enough to deflect particles with millions to billions of electron volts of energy. The physical shield approach must be thick enough that it still provides adequate protection when it has been eroded by trillions of particle impacts over decades of travel. Neither problem is obviously insoluble, but neither is easily solved, and both must be solved simultaneously with all the other problems. The fifth obstacle is time and its interaction with human biology and sociology. A 42-year journey to Proxima Centauri at 10% of the speed of light is on the border of the human lifetime. It requires crew members who are willing to devote most of their adult lives to a journey whose destination they will reach, if they survive, at very advanced age. The psychological and sociological challenges of confining a small group of human beings in a spacecraft for 4 decades Isolation, interpersonal conflict, monotony, the gradual erosion of connection to home are not engineering problems with physical solutions. They are human problems with no guaranteed solutions at all. The mental health literature on confined groups is not encouraging. Submarines, polar research stations, and long-duration spaceflight simulations all produce elevated rates of depression, anxiety, interpersonal conflict, and cognitive decline in ways that become more severe with increasing duration of confinement and decreasing resupply and communication. The biology of long-duration spaceflight is itself a serious research problem, not yet fully characterized even for missions measured in months rather than decades. In the absence of gravity, in the microgravity environment of a coasting spacecraft, when the engines are not burning and there is no thrust to simulate weight, the human body undergoes a complex series of adaptive changes, most of them harmful for long-term health. Bone density decreases at roughly 1 to 2% per month in the load-bearing bones, as the skeletal system responds to the absence of mechanical stress by down-regulating bone formation. Muscle mass decreases as muscles no longer need to support body weight. The cardiovascular system adapts to a fluid shift toward the upper body. In gravity, blood pools slightly toward the legs. In microgravity, it redistributes toward the head, causing a chronic congestion of the upper circulation that contributes to a syndrome called spaceflight-associated neuroocular syndrome, in which the pressure in and around the brain gradually increases and can cause irreversible structural changes to the optic nerve and retina, impairing vision. This syndrome has been observed in a significant fraction of astronauts who've spent 6 months or more on the ISS, and it has no fully effective countermeasure at present. The immune system is compromised in microgravity for reasons that are not yet fully understood, but that include alterations in the behavior of T cells and natural killer cells, the white blood cells responsible for identifying and destroying pathogens and abnormal cells. Reactivation of latent herpes virus infections, viruses that most humans carry in a dormant state after childhood exposure, including the Epstein-Barr virus and the varicella-zoster virus, is significantly more common in astronauts than in ground-based comparison populations, suggesting that immune surveillance of latent infections is less effective in the spaceflight environment. Gut microbiome composition changes in microgravity, sleep quality degrades. Circadian rhythms are disrupted by the absence of a natural day-night cycle governed by a planetary environment. A 42-year interstellar journey at nominal spaceflight conditions, coasting at constant velocity, with no continuous thrust to provide a gravity analogue, would subject the crew to these effects for 4 decades. The cumulative physiological changes after 42 years of microgravity would be beyond anything currently studied or characterized. Astronauts who have spent the longest continuous time in space, Valery Polyakov's 437-day mission on Mir, Mark van der Heij's 355-day mission on the ISS, show significant but largely reversible physiological changes on return. Whether the changes after 15 years, or 30, or 42 years are reversible or even survivable is unknown. The answer requires decades of study that we have not yet conducted. In an environment, deep interstellar space, far from the Sun's magnetic field, bombarded by galactic cosmic rays, that is significantly more hostile than low Earth orbit. The alternative, providing continuous 1G acceleration throughout the journey, solves the microgravity problem but requires the spacecraft to burn propellant continuously for 42 years. Except for a brief coasting period near the midpoint, where deceleration begins, the engines would need to operate without failure for the entire journey. No engine in human history has operated for 42 years continuously without maintenance, repair, or failure. The most reliable rocket engines ever built, the engines of long-duration spacecraft like Voyager, do not burn continuously. They fire briefly, providing short burns to adjust trajectory, and then shut down. Designing an engine that burns continuously for 42 years in the vacuum of interstellar space, with no maintenance capability, no replacement parts except those carried on board, represents a reliability engineering challenge of a kind that has never been attempted. Redundancy helps. Multiple engines, with backups for the backups, but each redundant engine adds mass, which adds full requirements, which adds more mess. The spiral is familiar. The communication problem is itself severe. At 4 light years, a message from Earth takes 4 years to arrive at the spacecraft, and any response takes another 4 years to return. Real-time communication is impossible. Any guidance, advice, medical consultation, or emergency support from Earth takes 8 years for a round trip. By the time Earth knows of an emergency and responds, the emergency is 8 years in the past. The crew is effectively on their own from the moment they leave the solar system, in a way that no previous human expedition has ever been. The most isolated expeditions in human history, Antarctic winter overcruise, early Antarctic expeditions before radio communication, sailors on circumnavigation voyages in the age of exploration were isolated for months, not decades. And they knew with reasonable certainty that rescue was possible in principle, that the gap between them and help was finite and crossable in human timescales. An interstellar crew would know that the gap is not crossable, that no rescue is conceivable, that whatever happens, they face it alone. The psychological requirements of such a mission are without precedent in human experience. Now let us step back from these 5 obstacles: the rocket equation, energy, deceleration, radiation, and human endurance, and ask whether any of the proposed solutions actually addresses them. Because proposals exist, and they deserve serious scrutiny rather than dismissal. The first and most technically developed proposal is laser sail propulsion, represented most concretely by the breakthrough Starshot project, announced in 2016 by Yuri Milner with $100 million in seed funding, and an advisory board that included Stephen Hawking, Freeman Dyson, and other serious scientists. The concept is straightforward in its physics: a ground-based array of lasers, generating an aggregate power of approximately 100 gigawatts, focuses its output on a thin reflective sail roughly a few meters across and a few grams in mass, including a grand-scale payload of electronics. The radiation pressure of the laser on the reflective sail accelerates it to approximately 20% of the speed of light in a matter of minutes. Sail then coasts to Proxima Centauri in roughly 20 years, conducts a brief flyby, and transmits its data back to Earth at the speed of light. Breakthrough Starshot addresses several of the obstacles we have discussed. The spacecraft carries no propellant. The rocket equation does not apply, because the energy is provided by the laser system at Earth. The mass is gram scale rather than ton scale, which dramatically reduces the energy required for a given velocity. The journey time of 20 years is within a human lifetime, making it possible for the people who launch the probe to receive the data in their own lifetimes. The absence of deceleration simplifies the mass requirements at the destination, though it means the encounter with the target system is limited to a few hours of closest approach at 20% of light speed. But the engineering challenges are extraordinary, and several of them may be insurmountable. The 100 gigawatt laser array required to accelerate the sail is roughly 10,000 times more powerful than any laser ever built. The world's most powerful lasers, pulse, laboratory scale, used for fusion research, achieve petawatt power levels, but only for femtoseconds, quadrillionths of a second. Sustained 100 gigawatt illumination for the minutes required to accelerate the sail is a completely different kind of engineering challenge, requiring a coordinated array of thousands of individual laser units, precise phase locked so their outputs add coherently rather than destructively, aimed with sufficient precision to keep the beam focused on a meter-scale sail thousands of kilometers away, and then, as the sail accelerates away, millions of kilometers away, and eventually billions of kilometers away, the beam diverges as it travels. A laser beam cannot be focused to a perfect point at large distances because diffraction, the spreading of coherent light waves, is unavoidable. The angular resolution of the beam is set by the ratio of the wavelength to the diameter of the transmitter. A 1 kilometer laser array, transmitting at 1 micron wavelength, has an angular resolution of roughly 10 to the power of 9 radians, producing a beam that is about 10 meters wide at a distance of 10 million kilometers. Keeping a few meters sail within this beam, as the sail accelerates rapidly and its trajectory deviates from prediction by small amounts, requires a beam steering capability and positional tracking precision that exceed anything currently available. The sail material must be extraordinarily thin and highly reflective. It must reflect nearly all the laser energy incident on it. Absorbing even a fraction of a percent would heat it to temperatures that destroy it in seconds, given the laser intensities involved. Online, we will have a lot of weight. The sail must be thinner than 100 nanometers, thinner than a human cell membrane, while maintaining mechanical integrity under the intense radiation pressure and thermal gradients during acceleration. No material currently known has all these properties simultaneously. The candidate materials, thin films of aluminum, silicon carbide, or more exotic layered materials, are active areas of research. But the engineering of a sail that survives the acceleration phase and then survives decades of cosmic ray bombardment in interstellar space is not a solved problem. The gram-scale payload, the actual probe electronics, must contain a camera or other sensor, a data storage system, a power source, a transmitter, and all associated processing electronics in a package massing a few grams. This is a miniaturization challenge of extraordinary severity. Current nanosatellites, the smallest operational spacecraft, mass hundreds of grams and are significantly less capable than what a Starshot probe would require. Fitting adequate scientific instruments, power storage, and a transmitter powerful enough to send data 4 light-years back to Earth, all within a gram, requires technology well beyond the current state of the art in microelectronics and integrated power systems. The communication challenge is particularly acute. The probe must transmit its data from Proxima Centauri, 4 light-years away, using a transmitter that masses a fraction of a gram and is powered by a power source that also masses a fraction of a gram. The signal power available is milliwatts or less. The signal must cross 4 light-years and be detectable at Earth. The square of the distance means the signal power at Earth is approximately 10 milligrams of the transmitted power. So a 1 milliliter transmitter delivers about 10 milligrams of the transmitted power, requiring a receiving antenna of truly enormous size and sensitivity to detect any signal at all. Breakthrough Starshot's proponents have noted that a future Earth-based laser facility capable of 100 gigawatts could also serve as a powerful receiving telescope, but the signal-to-noise challenge remains formidable. And there is the fundamental constraint that was easiest to state and hardest to engineer away: no deceleration. The probe flies through the Proxima Centauri system at 20% of the speed of light, spending perhaps an hour within a few astronomical units of the star, passing by a potential planet in seconds. 1 second of data collection. 1 second to photograph, to measure, to detect whatever might be detected. Then gone, continuing into interstellar space. Whatever the probe finds, whatever remarkable thing it might detect, it finds it in seconds and then never returns to it. This is reconnaissance, not exploration. It is a snapshot, not a study. It is better than nothing, considerably better than nothing, and the data transmitted back over years would be genuinely valuable. But it is not a foothold. It is not a step toward anything further. It is a single snapshot of the nearest stellar system, taken from a speeding probe that cannot slow down, cannot investigate more carefully, cannot follow up. Everything the probe finds that raises new questions goes unanswered. A more ambitious class of proposals involves nuclear propulsion, and specifically the concept studied with greatest rigour in the Project Daedalus feasibility study conducted by the British Interplanetary Society between 1973 and 1978. Daedalus was designed as an uncrewed flyby probe to Barnard's star, 5.9 light-years away. Using a fusion rocket powered by inertial confinement fusion of pellets of deuterium and helium-3. The design specified a two-stage vehicle massing 54,000 tons at launch, with 50,000 tons of fuel, achieving a final velocity of about 12% of the speed of light and reaching Barnard's star in about 50 years. The design was serious and detailed, carried out by professional engineers and scientists. Its conclusions were sobering. The first stage engine required 250 deuterium helium-3 pellets per second, each pellet compressed by a ring of electron beam guns to conditions sufficient for fusion ignition. The reliability and precision required: each pellet must be ignited within milliseconds of the previous one. The timing and energy deposition must be controlled with extraordinary precision. For the entire 2-year burn of the first stage were beyond 1978 technology. They may be beyond current technology. Sustained inertial confinement fusion ignition itself remains a research challenge. Achieving it 250 times per second for 2 years consecutively in a spacecraft engine is a vastly greater challenge than laboratory demonstration. The helium-3 fuel requirement was equally sobering. Approximately 30,000 tons of helium-3 would be needed. The Earth's entire known reserves of helium-3 amount to a few hundred kilograms, enough for a few minutes of Daedalus running at full power. The Daedalus study proposed mining helium-3 from the atmosphere of Jupiter, using mining facilities that do not exist, to extract quantities of helium-3 that require mining the atmospheres of gas giants at industrial scales. This is not a near-term proposition. It is the kind of industrial enterprise that a spacefaring civilization might undertake a century or more from now, with fully established infrastructure in the outer solar system. It is a requirement that places Daedalus in the category of theoretically possible, with vastly greater technological capability than we currently have, rather than achievable in the foreseeable future. The Project Longshot design, a subsequent US study, proposed a smaller unmanned probe to Alpha Centauri using nuclear pulse fusion propulsion, reaching a final velocity of about 5% of the speed of light and arriving in approximately 100 years. It required energy and fuel in quantities similarly beyond current production capabilities. The Project Icarus study, a 21st century update to Daedalus, refined the concept and confirmed that the fundamental challenges remain the same: the fuel requirements, the fusion ignition engineering, and the deceleration problem for anything intended to stop rather than fly through. What all these studies share is a consistent conclusion that reaches across different approaches and different vehicle designs. The fundamental obstacles are not ones that better engineering alone can solve. They require either new physics, new phenomena that allow propulsion at velocities close to light without the mass ratios demanded by the rocket equation, or new civilization-scale infrastructure that currently does not exist and cannot be built. With our current energy and industrial capacity, better engineering, in the conventional sense of applying known physical principles with greater skill, gets us perhaps to a few % of the speed of light over the course of a century. It does not get us to the kind of velocities that make interstellar travel a human-scale endeavour, and it does not solve the energy problem for any mission that must decelerate at its destination. The mention of new physics requires that we be specific about what the candidate new physics actually looks like, and why each candidate faces serious problems. There are two main categories of speculative but physics-grounded proposals that could, in principle, circumvent the speed of light and energy barriers: wormholes and warp drives. Both are solutions to Einstein's general relativity equations. Both permit something functionally equivalent to faster-than-light travel, and both face obstacles that, as of current physics, appear to be fundamental rather than merely technological. A wormhole, technically an Einstein-Rosen bridge, is a solution to general relativity's field equations that describes a tunnel connecting two distant regions of space-time. If such a tunnel could be traversed, an object could pass through it and emerge at a distant location without travelling through the intervening space. The journey through the wormhole might take seconds, while thousands of light years of normal space were bypassed. Einstein and Nathan Rosen derived the solution in 1935, but the original Einstein-Rosen bridge was not traversable. It collapsed too quickly for anything to pass through. In 1988, Kip Thorne and colleagues at Caltech analysed the conditions under which a stable, traversable wormhole could exist, and their conclusion was unambiguous. A traversable wormhole requires matter with negative energy density, matter whose energy per unit volume is less than 0, to hold it open. The exotic matter must line the throat of the wormhole, exerting a repulsive gravitational effect that prevents the tunnel from collapsing. Negative energy density is not impossible in quantum mechanics. The Casimir effect, the force of attraction between two closely spaced, uncharged metal plates, arises from a suppression of quantum vacuum fluctuations between the plates, which produces a region of lower than vacuum energy density, technically negative with respect to the vacuum. This has been measured experimentally, but the amount of negative energy produced by the Casimir effect is negligibly small, on the order of 10⁻⁶ joules per square meter for plates separated by a micron. The amount of negative energy required to hold open a traversable wormhole, large enough for a spacecraft to pass through, has been estimated at roughly the equivalent of a Jupiter mass of negative energy. The gap between what quantum mechanics produces in laboratory conditions and what a traversable wormhole requires is a factor of roughly 10. Not a factor of 10, not a factor of a million, 10. There is no known mechanism and no theoretically proposed mechanism with any experimental grounding that bridges this gap. There are also quantum gravity constraints that some physicists believe make traversable wormholes theoretically impossible, not merely impractical. The conjectured connection between traversable wormholes and quantum entanglement the EREPR conjecture, proposed by Juan Moldacena and Leonard Susskind in 2013, suggesting that entangled particles are connected by tiny wormholes, is theoretically intriguing but does not obviously help with the traversability problem. The wormholes in the EREPR picture are not traversable by any object, including information. The warp drive, proposed in 1994 by Miguel Alcubierre, avoids the wormhole's traversability problem by instead proposing to move a bubble of space-time with the spacecraft inside the bubble faster than light, without requiring the spacecraft itself to move faster than light through local space. The spacecraft floats inside the bubble, which contracts space in front of it and expands space behind it, effectively surfing a wave of space-time distortion to any destination at any speed. The physics of the bubble's interior is entirely normal. No time dilation for the crew, no acceleration, no violation of special relativity locally. The faster-than-light aspect is entirely in the motion of the bubble wall itself, which is space moving, not an object moving through space. Alcubierre's metric is a valid solution to general relativity's equations. The mathematics is impeccable. The problem, again, is the energy. Maintaining the warp bubble requires negative energy density in the bubble wall. The original Alcubierre calculation required a quantity of negative energy comparable to the mass energy of Jupiter, but with a negative sign. Subsequent work by Harold White at NASA, published around 2012, suggested that modifying the geometry of the bubble using a donut-shaped bubble rather than a spherical one, and oscillating the bubble wall's thickness, could potentially reduce the required negative energy by many orders of magnitude, possibly to quantities achievable with near-future technology. White's claims generated significant media attention, and some experimental work at Matters Eagleworks Laboratory, searching for microscopic space-time distortions caused by test configurations intended to produce small warp effects. No warp effect has been detected. The theoretical work supporting large reductions in required negative energy has been questioned by other physicists, who argue that White's calculations contain errors or rely on assumptions that are not physically justified. The consensus in the physics community is that Alcubierre drives remain far outside the realm of achievable engineering, and that the negative energy requirements, while possibly smaller than originally calculated, are still so large as to be effectively impossible with any plausible physical mechanism. The enthusiastic media coverage of White's work notwithstanding, no warp drive has been demonstrated. No theoretical pathway to achieving the required negative energy at spacecraft scales exists, and the experimental searches at Eagleworks found no warp effect. It is also worth noting that even if warp drives were achievable, they would face a control problem. A ship inside a warp bubble cannot send signals outside the bubble to control or modify it, because any signal would have to travel through the wall, which is moving faster than light. The crew inside the bubble cannot steer, cannot stop, cannot modify the trajectory. They are passengers in a bubble they cannot control from the inside. The engineering of a warp drive that can actually navigate to a specific destination, rather than just travelling in a general direction, requires solving this communication problem, which appears to be fundamental. In the absence of new physics, wormholes or warp drives or some third option not yet imagined, the interstellar travel problem reduces to the problems we have already described: impossible energy requirements for realistic vehicles, crushing mass ratios for any rocket architecture, century-scale journey times even for the most optimistic propulsion concepts, and the biological and psychological impossibility of keeping a human crew alive and functional for such durations. This is where the argument becomes genuinely sobering. Because there are people who respond to all of these challenges by saying, "Of course it is hard now, but technology always advances, and given enough time, enough ingenuity, what seems impossible today becomes achievable." This is true as a historical statement. We have repeatedly solved problems that seemed intractable. But there is a category error in applying this general observation to interstellar travel, because the obstacles here are not primarily problems of insufficient ingenuity or insufficient technology. They're consequences of specific physical laws: the finite speed of light, the conservation of momentum, the limited energy density of nuclear reactions, the inverse square law for radiation intensity over distance. That technology cannot change, only work around. And working around them, for the specific problem of sending a crewed spacecraft to another star in a human lifetime, requires not improvements within existing physics, but either new physics or a kind of civilization-scale mobilization of resources that makes the Manhattan Project look like a garage workshop. Consider the energy problem in this light. The total current energy output of human civilization is roughly 2 times 10,013 watts, 20 terawatts. To accelerate a 1,000-ton spacecraft to 10% of the speed of light, sufficient for a 42-year journey to Proxima Centauri, requires approximately 4.5 times 10 squared joules. At current global energy production rates, generating this much energy would take approximately 700 years. Not building the spacecraft, not operating the mission, just generating the energy required to propel the spacecraft, assuming perfect conversion efficiency from energy source to kinetic energy, which is itself an idealization. A civilization that mobilized all its energy production for 700 years and dedicated all of it to a single interstellar mission would succeed in launching one probe to the nearest star. That is the scale of the problem. It is not a scale that responds to more research and development. It is a scale that demands either orders of magnitude increases in civilizational energy production or fundamentally new physics that changes the energy requirements. Could we increase global energy production by the necessary orders of magnitude? In principle, yes. The Sun radiates approximately 3.8 times 10 squared to 6 watts, roughly 10 trillion times current human energy production. A civilization that could capture even 1% of the Sun's total energy output would have 100 billion times more power than we currently use, making the energy requirements for interstellar propulsion trivial by comparison. Freeman Dyson's thought experiment of a Dyson sphere, a structure surrounding the Sun at Earth's orbital radius, capturing all solar output, would provide the energy. A more modest Dyson swarm, capturing only a small fraction of the Sun's output, would suffice for interstellar propulsion. These are not physically forbidden concepts. They are merely civilization-scale engineering projects of a difficulty and duration that no human institution has ever attempted or can currently plan for. The fundamental question is, can human civilization grow and sustain itself to the point where such projects become possible without destroying itself first? This is not a question physics can answer. It is a question about the trajectory of civilization, about whether the social, political, and ecological challenges of the coming centuries can be managed well enough to allow the continuous technological progress that interstellar travel ultimately requires. The history of civilizations is not uniformly encouraging on this point. Civilizations collapse, technologies are lost. Knowledge accumulated over centuries can be erased in generations. There is no physical law that guarantees the continuous advancement of human civilization, and the obstacles to interstellar travel are so large that they require civilization-scale effort sustained over centuries, not decades, to overcome. There is, in this context, a class of proposals that attempts to sidestep the crude spaceflight problem entirely by replacing human travelers with artificial intelligence and self-replicating robotic systems. The von Neumann probe concept, a spacecraft that arrives at a target star, uses local resources to build copies of itself, and sends those copies to further targets, in principle, allows galactic exploration without the biological constraints of human travel. A von Neumann probe need not arrive quickly. It need not protect biological tissue from radiation. It need not solve the psychology of confinement. It need only survive the journey and function at the destination. These requirements are demanding, but not subject to the same absolute constraints as crude travel. The concept has a rigorous mathematical foundation. John von Neumann, the legendary mathematician who contributed foundational ideas to game theory, quantum mechanics, computer architecture, and nuclear weapons design, developed the theoretical framework for self-replicating automata in the 1940s and 1950s. He proved that a sufficiently complex machine can, in principle, construct a perfect copy of itself from raw materials, given a set of instructions that is itself part of what gets copied. This is not merely a theoretical curiosity. It is, in effect, what living cells do. DNA encodes the instructions for building the machinery that reads DNA and uses it to build more machinery that reads DNA. Life is von Neumann's self-replicating automaton, implemented in carbon and water by 4 billion years of evolution. A technological von Neumann probe would be a machine capable of locating the raw materials available in a new stellar system, asteroids, comets, planetary bodies, mining and processing them, using the processed materials to construct a copy of itself, and programming that copy to travel to the next target. The exponential mathematics of replication means that a fleet of von Neumann probes, launched initially as a single probe, could potentially colonize the entire galaxy on timescales of millions of years, far shorter than the galaxy's age. Each generation of probes spawns multiple new probes. The fleet grows exponentially. The galaxy fills. The technology required is daunting. The probe must carry a complete set of instructions for building itself, a blueprint of extraordinary complexity. It must carry the manufacturing capability to process raw materials from an alien stellar environment, which may differ significantly from the solar system in its composition and structure. It must be capable of autonomous decision-making at a level far beyond anything current artificial intelligence can achieve, because it will face novel situations that no programmer could anticipate. It must be robust against failure over journey times of decades to centuries, with no possibility of maintenance or repair from Earth. It must be small enough to be launched, at reasonable cost, and with manageable propulsion requirements, yet complex enough to replicate itself at the destination. These requirements are in tension. Complexity and compactness do not easily coexist, and the engineering of a self-replicating interstellar probe is, if anything, harder than the engineering of a crude interstellar vessel, despite the absence of biological passengers. There is also a deeper question about the nature of what a von Neumann probe represents as a means of exploration. The probes that arrive at distant stellar systems are not the probe that was launched. They are copies of copies of copies, machines whose instructions have been replicated perhaps dozens of times, in environments where cosmic ray damage could corrupt the replication, where manufacturing variations could introduce errors, where the evolutionary pressures of different stellar environments could cause the probe's capabilities to drift in unpredictable ways. The relationship between the civilization that launched the first probe and the probes that arrive at distant stellar systems centuries later may be no more intimate than the relationship between a parent and a very distant descendant who shares the parent's genes, but not the parent's experiences, values, or memories. The limitations of the von Neumann probe concept are different in character from the limitations of crude travel. They are limitations of purpose and value rather than physics. A self-replicating probe can visit other stellar systems. It cannot form a human connection with them. It cannot be inspired by what it finds. It cannot bring back the experience of standing under an alien sky. If the goal of interstellar travel is exploration in the deepest sense, the kind of exploration that changes who we are by exposing us to what we did not know, then a robotic proxy is not a substitute. It is a tool, a useful one, but not the thing itself. And even robotic probes face the communication problem. At 4 light-years, any data transmitted by a probe at Proxima Centauri takes 4 years to arrive. At the distances of most other interesting stellar systems, hundreds or thousands of light-years, the delay is centuries or millennia. A probe that explores a stellar system 1,000 light-years away and transmits its findings home cannot be directed in any interactive way, cannot respond to instructions, cannot be told to look more carefully at the interesting thing it found. It must be fully autonomous from the moment of launch, making all decisions independently, because any instruction from Earth takes 1,000 years to arrive, and any response to those instructions takes 1,000 years to return. The probe must be, in this sense, more than a machine. It must be, in some sense, an explorer capable of judgment, curiosity, and independent scientific reasoning. Whether such a machine is possible is a question for a different field of science, and the answer that field is currently converging on is possibly yes, eventually, but not soon. And not without confronting profound questions about what machine intelligence can and cannot do that remain unresolved. Now let us consider the most optimistic framing of the entire problem, because intellectual honesty requires that too. The optimistic case rests on a combination of observations. First, the history of physics has repeatedly revealed that phenomena we did not know existed opened up new possibilities we could not have anticipated. Electromagnetism, discovered in the 19th century, enabled the telecommunications revolution that no one in 1800 could have predicted. Quantum mechanics, developed in the 20th century, enabled semiconductor electronics and lasers that would have been incomprehensible to Newton or Maxwell. Nuclear physics, also 20th century, enabled both weapons and power plants of a kind that even Maxwell's equations could not have hinted at. If the history of physics tells us anything, it tells us that our current understanding of the universe is incomplete, that there are phenomena yet undiscovered that will expand our technological capabilities in ways we cannot currently predict. Could there be undiscovered physics that makes interstellar travel more tractable? Specifically, could there be some mechanism that allows travel at superluminal speeds, or something functionally equivalent? The honest answer is, we cannot rule it out, but we have no evidence for it, and the theoretical landscape of physics, as currently understood, is not encouraging. General relativity does permit, in principle, solutions to its equations that would allow faster-than-light transit through space, wormholes, Alcubierre warp metrics, but both require exotic matter with negative energy density at scales that quantum field theory suggests cannot be achieved. String theory, the most developed candidate for a quantum theory of gravity, has produced some ideas about exotic physics at very small scales, but nothing that obviously translates to macroscopic faster-than-light travel. The search for physical loopholes in the light-speed barrier has been active and intense for decades, and the loopholes, when found, have invariably been either non-traversable, requiring negative energy in impossible quantities, or subject to quantum constraints that close them. This does not prove that no such physics exists. Absence of evidence is not evidence of absence. But it does mean that the hope for new physics to solve the interstellar travel problem is not a hope grounded in any specific theoretical indication. It is a hope grounded in the general observation that physics has surprised us before. That is a real basis for hope, but it is a thin one to build a civilization's interstellar ambitions on. The second element of the optimistic case is the observation that the problem does not require a single breakthrough, but rather the compounding of many incremental improvements over very long timescales. If human civilization persists for another 1,000 years, a plausible scenario, not guaranteed but not implausible, the energy production, materials science, computing, and aerospace engineering of a civilization 1,000 years more advanced than ours will be as incomprehensible to us as our current technology would be to a medieval scholar. A civilization capable of mining the outer solar system for fusion fuel, of constructing a square kilometre laser array in space, of building spacecraft with reliability and longevity measured in decades rather than years, of developing artificial intelligence capable of autonomous scientific research, such a civilization might find the interstellar travel problem not solved, but significantly less severe. Not by violating physics, but by having the resources and technology to work closer to the physical limits. This is the argument that the most thoughtful advocates of interstellar travel make. Not that it is easy, or that we are close, or that the obstacles are merely engineering challenges waiting for the next generation of engineers, but that the timescales of civilizational development and the timescales of interstellar travel are actually compatible, that the centuries required to develop the necessary technology are not incompatible with the centuries required for the journeys themselves. A civilization that begins serious work on interstellar propulsion today, even at the level of theoretical research and small-scale experiments, might expect to have flyby probes reaching the nearest stars within a few centuries, crewed missions within a millennium, if the civilization survives and continues to develop. This argument is plausible, but carries its own sobering implication. A millennium is 40 generations. 40 generations of scientists and engineers and policymakers maintaining the same institutional commitment to the same long-term goal across changes of government, culture, language, economic system, and civilization. There has never been a human institution that maintained a single coherent goal across 40 generations. The longest-running institutions in human history, the Catholic Church, certain universities, certain monastic traditions, are perhaps 1,000 years old, but they have changed enormously over that time, repeatedly abandoning old goals and adopting new ones in response to changing circumstances. The idea of a 40-generation scientific program maintained with consistent purpose is without precedent in human history. And this is where the question of interstellar travel connects to one of the deepest questions about the long-term future of our civilization, the question of existential risk. An existential risk is any threat that could permanently and drastically curtail humanity's long-term potential, not just setting us back by decades or centuries, but ending our civilization or our species entirely, or reducing us to a permanent state of technological and demographic decline from which recovery is impossible. The candidates are familiar: nuclear weapons and nuclear war, engineered biological weapons capable of pandemic-level lethality beyond anything natural, catastrophic climate change, asteroid impact, supervolcanic eruption, and the emerging risks associated with advanced artificial intelligence. The connection to interstellar travel is this: the technological development needed to make interstellar travel possible requires centuries of uninterrupted scientific and industrial progress. But each decade of progress also creates new existential risks, new weapons, new pathogens, new systems of sufficient complexity that their failure modes are not fully understood or controlled. The same civilization that develops fusion reactors powerful enough to propel interstellar probes also has the capacity to engineer pandemic viruses or to build autonomous weapon systems of extraordinary lethality. The same advances in materials science that enable ultralight, ultra-thin laser sails also enable new forms of structural failure in critical infrastructure. Technological progress is not unambiguously safe, and the long time frames required for interstellar travel development increase the number of opportunities for catastrophic civilizational setback. This is not an argument for halting technological progress. It is an argument for taking existential risks seriously as a constraint on the probability of interstellar travel ever occurring. If the probability of catastrophic civilization collapse in any given century is, say, 5%, then the probability that civilization survives for 10 centuries, the minimum needed for any realistic interstellar capability, is 0.95 to the power of 10. Approximately 60%. Not terrible. But if the probability of catastrophic collapse is 10% per century, a figure that some researchers consider conservative given the range of emerging risks, the probability of 10-century survival drops to 0.90 to the power of 10, roughly 35%. And for 20 centuries, 12%. 30 centuries, 4%. The mathematics of compounding risks over long timescales is harsh, and the timescales required for interstellar travel are very long. The philosopher Nick Bostrom and others working in existential risk studies argue that the long-run future of intelligence, whether human or post-human or artificial, is the most important variable in assessing civilizational priorities. A civilization that achieves interstellar travel and spreads to other stellar systems has, in principle, ensured its long-term survival against any single planet's catastrophe. The stars become a hedge against extinction. But to reach the stars, the civilization must first survive the technological adolescence, during which the tools of potential self-destruction are developed alongside the tools of potential expansion. The filter, the bottleneck, may lie not in the stars themselves, but in the centuries between here and the first interstellar launch. This connects directly back to the Fermi paradox. If civilizations commonly develop the capability for interstellar travel, and if the galaxy is old enough that many civilizations have had time to develop this capability, then where are they? The silence of the sky, the absence of detected signals or artifacts from other technological civilizations, is one of the most puzzling facts in science. It is consistent with many explanations, including the possibility that we are genuinely the first technological civilization in the Milky Way, or that technological civilizations are far rarer than optimistic estimates suggest, or that the journey to interstellar travel is a filter that most civilizations fail to pass. Not because the physics is too hard, the physics permits it, but because the social, political, and existential risks of the technological development phase destroy civilizations before they achieve the capability. If this interpretation of the Fermi paradox is correct, then the question of whether we will ever reach another star is intimately connected to the question of whether we will survive the coming centuries with our civilization intact. The stars are not the obstacle, we are. The physics permits the journey, the biology can be engineered around, given enough time and research. The energy can be produced, given enough civilizational development. The real constraint is whether the civilization that needs to do all of this continues to exist, to prioritize it, to resist the temptations and risks that advanced technology creates, long enough to reach the launch window. The optimistic reading of our current moment is that we are the first civilization to become genuinely aware of these existential risks and to begin taking them seriously as a category of problem requiring concerted human effort. The field of existential risk studies, the growing attention in governments and research institutions to biosecurity, AI safety, and climate change, these are signs that we are at least trying to navigate the filter, not blindly walking into it. Whether we succeed is not guaranteed, but the attempt is underway. And if the attempt succeeds, if we navigate the coming century without catastrophe, establish a more resilient and distributed civilization, develop the energy and technology needed for serious interstellar propulsion research, then the question of whether we will ever reach another star shifts from probably not to possibly yes, on a timescale of centuries to millennia. That is not a comforting answer in the sense of yes, soon we will be among the stars. It is a comforting answer only in the sense of if we are wise enough and lucky enough to survive, the physics commits it. The universe has not closed the door. It has simply made the price very high and demanded that we pay it not in a single generation's effort, but in the sustained compounding work of many generations, each building on the last, each resisting the risks that their own technology creates, each keeping faith with a goal that none of them will personally achieve. This is, perhaps, the most human thing imaginable. And there is a third element of the obstacle that goes beyond physics and engineering entirely. The question of what reaching another star would mean, and whether the thing that arrives bears any meaningful relationship to the civilization that sent it. We have touched on this in the context of multi-generational ships and relativistic time dilation, but it deserves emphasis here. Any mission to the nearest star that takes decades will return data to a civilization that is decades different from the one that launched. Any mission that takes a century returns to a civilization that may be unrecognizable. Different language, different government, different values, different scientific questions. A mission to Proxima Centauri launched today would return its first data in 8 years if the probe travelled at the speed of light itself. At 10% light speed, the data would return in 84 years. The civilization that built the probe might find the data deeply valuable. More likely, the civilization 84 years from now will have priorities and questions so different that data collected by a probe designed today will be of historical rather than scientific interest. The equivalent of asking how useful the data from the 19th century balloon flight would be to a 21st century atmospheric scientist. This is not a reason not to try. Some knowledge is worth accumulating regardless of when it is used, but it does undercut the framing of interstellar travel as a near-term civilizational priority. If the data arrives a century after the probe launches, the probe's design must be right the first time without any correction for the scientific questions of the future. If the crewed ship arrives at Proxima Centauri 50 years after launch, and the crew transmits their findings home, those findings arrive 50 years after that, a century after departure, in a civilization that may not care, or may already know more from a generation of successor probes launched in the intervening decades with better technology. The interstellar mission exists outside the normal feedback loop of science, where results guide new experiments, guide new results. It is a one-shot commitment to the questions of today, delivered to the civilization of tomorrow. All of this paints a picture that is, for anyone who has grown up on the inspiring vision of humanity as a spacefaring species, spreading through the galaxy, genuinely sobering. But let us be precise about what it does and does not say. It does not say that interstellar travel is physically impossible. The laws of physics permit spacecraft to travel to other stars. They permit the journey to take decades or centuries in ship time under continuous acceleration. They permit the creation of communication systems that transmit data across 4 light years. None of these are forbidden. They are merely extraordinarily demanding. What the analysis does say is this: the gap between where we are and where we need to be is not a gap that fills in the next generation or the next several generations. The energy problem alone, independent of all the engineering challenges, requires a civilizational transformation in energy production that will take centuries at minimum. The propulsion technology required for any crewed mission is beyond the current state of the art by orders of magnitude. The material science, the life support systems, the autonomous guidance and navigation, the communication infrastructure, the deceleration technology, each individually represents a challenge at the frontier of engineering. Together, they represent a challenge that probably requires a civilization significantly more advanced than ours in terms of total energy production and technological capability to meet. We might get there. There is nothing in physics that says we will not. But there is also nothing in physics that says we will. The universe does not owe us the stars. It simply makes them possible under conditions that it does not make easy to meet. Whether we meet those conditions depends on choices we have not yet made, on crises we have not yet faced, on scientific discoveries that have not yet occurred, on civilizational trajectories that no one can predict with confidence. The nearest star is 4.24 light-years away. It has been 4.24 light-years away for the entire existence of our species, and it will be approximately 4.24 light-years away for as long into the future as we can reasonably project. Its distance is not changing in any way that matters on human timescales, though the two stars are gradually approaching each other and will be only about 3.11 light-years apart in roughly 26,700 years. In that window, in the next 26,700 years, when Proxima is at its closest approach to our solar system, if we have developed the technology, we have the best opportunity humanity will see for hundreds of thousands of years. That is a real timescale. Not a comfortable one for human planning, but a real one. Proxima Centauri b, the potentially habitable planet orbiting Proxima Centauri, in its habitable zone, announced in 2016, based on radial velocity measurements and confirmed in subsequent observations, orbits its red dwarf host at a distance of about 0.0485 astronomical units, completing one orbit in approximately 11.2 days. It has a minimum mass of roughly 1.07 Earth masses, consistent with a rocky planet. It orbits in the habitable zone, the range of distances from a star at which liquid water can exist on the surface of a planet with an appropriate atmosphere for its host star. The existence of this planet, sitting in the habitable zone of the nearest star, was the most exciting exoplanet discovery of the 2010s, and it has given interstellar travel advocacy a concrete destination with genuine potential interest. But Proxima Centauri b's habitability is deeply uncertain, and understanding why requires understanding the character of red dwarf stars. Red dwarfs, the most common type of star in the galaxy, making up roughly 70% of all stars, are small, dim, and extraordinarily long-lived. While our Sun will exhaust its hydrogen fuel in approximately 5 billion more years, a red dwarf of Proxima's mass will continue burning hydrogen for approximately 4 trillion years. nearly 300 times the current age of the universe. In principle, the long lifetimes of red dwarfs give any orbiting planets an extraordinary amount of time for life to develop. In practice, the early lives of red dwarfs create serious problems for habitability. Young red dwarfs are ferociously active. They emit powerful flares, sudden releases of energy, including ultraviolet and X-ray radiation, from the magnetic activity of their convective interiors at rates and intensities far exceeding anything our own Sun produces. Proxima Centauri is a flare star. It regularly produces flares that, in terms of their ultraviolet output, can temporarily increase the UV flux of Proxima B's surface by factors of hundreds or thousands, doses that would be lethal to surface life on Earth without adequate ozone shielding. And that would gradually erode the ozone layer of any planet not continuously resupplied by volcanism or other atmospheric processes. The habitability of Proxima b depends critically on whether it has a substantial atmosphere, whether that atmosphere can survive the flare bombardment over billions of years, and whether the atmospheric composition includes species capable of shielding the surface. There is also the tidal locking problem. Proxima b orbits at 0.0485 AU, 1/20th the distance from Earth to the Sun, about 7 million kilometers. At this close range, the tidal forces exerted by the star on the planet are strong enough to have synchronized the planet's rotation with its orbital period, just as the Moon's rotation has been synchronized with its orbital period around Earth, such that the same face always points toward us. Proxima b is almost certainly tidally locked, one hemisphere permanently facing the star, bathed in continuous light, the other hemisphere in permanent darkness. The temperature differential between the permanent day side and the permanent night side could be extreme, driving ferocious atmospheric circulation and potentially causing atmospheric gases to condense and freeze out on the cold night side. Whether any atmosphere could survive in a stable state, and whether any surface liquid water could persist in such a regime, is deeply uncertain and the subject of active climate modelling research. The most detailed models of Proxima b's climate suggest that, under certain conditions, particularly with a thick atmosphere capable of redistributing heat, and with a carbon silicate cycle that regulates atmospheric carbon dioxide, liquid water could persist on the planet's surface, concentrated in a roughly circular region on the day side. This is not an implausible scenario, but it requires assuming a particular atmospheric composition and circulation that we cannot currently confirm from 4 light-years away. We do not know whether Proxima b has an atmosphere at all. We do not know whether it ever had one, or whether the stellar activity stripped it away early in the system's history. The planet may be a bare, irradiated rock. It may be a world with a stable climate and liquid oceans. We genuinely do not know. What we do know is that the answer matters enormously, not just for interstellar travel advocacy, but for the most profound scientific and philosophical question we can ask: are we alone? If Proxima b is habitable, and if life arose there as it arose on Earth, then the nearest star hosts life. Life would be present in 2 of the 2 nearest stellar systems to the Sun, a statistical distribution that would strongly imply that life is common throughout the galaxy. The implications for everything from astrobiology to theology to our understanding of our own place in the universe would be staggering. And if Proxima b is lifeless, a sterile rock in the habitable zone of a flare star, that too is important information about the conditions under which life can and cannot arise. Getting the answer requires either a spacecraft flyby or a sufficiently powerful telescope. The telescope option is in the near term the more achievable. A space telescope with a mirror diameter of perhaps 6 to 10 meters equipped with a coronagraph capable of suppressing the glare of Proxima Centauri to a level that allows the planet's reflected light to be detected, and with a spectrograph sensitive enough to detect the molecular absorption features of atmospheric gases in the reflected spectrum. Such a telescope could, in principle, determine whether Proxima b has an atmosphere containing oxygen, water vapor, carbon dioxide, or methane. None of these detections would prove life is present. They would each require careful interpretation. But detecting atmospheric oxygen at concentrations comparable to Earth's would be, to most astrobiologists, strong evidence of biological activity. Because abiotic processes tend to remove oxygen from planetary atmospheres rather than produce it in large quantities. The NASA Habitable Worlds Observatory, a flagship-class space mission currently in the early stages of concept definition, is designed specifically to directly image and spectroscopically characterize Earth-like planets in the habitable zones of nearby stars. It is not yet funded or scheduled for launch, but it represents the scientific community's recognition that the question, "Does Proxima b have life?" is answerable without physically going there, given sufficient telescope capability. The telescope required is large. Its mirror needs to be large enough, and its coronagraph needs to be precise enough to detect a planet 10 to 100 million times dimmer than its host star at a separation of a fraction of an arc-second. But it is not beyond current engineering. It is a matter of funding and priority, not a matter of new physics. JWST has begun attempting atmospheric characterization of nearby exoplanets, including some orbiting red dwarfs similar to Proxima Centauri. The results so far suggest that some planets in these systems have lost their atmospheres due to the intense stellar activity. Whether Proxima b retains an atmosphere capable of supporting liquid water remains an open question that current instruments may not be able to answer definitively. Future observatories, including proposed extremely large space telescopes designed specifically for direct imaging and spectroscopy of nearby exoplanets, such as the Large Ultraviolet Optical Infrared Surveyor or the Habitable Worlds Observatory, may provide the answer within decades without requiring a spacecraft to cross the 4 light-year gap. And this brings us to the most important insight about the entire question of reaching another star. The value of the stars is not only in physically visiting them. Most of what science wants to know about nearby stellar systems can, in principle, be learned from here, from sophisticated telescopes that can analyze the light from exoplanet atmospheres, detect the signatures of biology in the spectra of distant worlds, map the structure of stellar systems in 3 dimensions, and characterize the environments of nearby stars in exquisite detail. We do not need to travel to Proxima Centauri to determine whether Proxima b has an oxygen-rich atmosphere. We need only a large enough telescope with a coronagraph capable of suppressing the glare of the host star enough to detect the planet's reflected light, and a spectrograph sensitive enough to identify the molecular signatures in that light. That telescope does not yet exist, but it is not beyond the engineering capabilities of the coming decades. It costs billions of dollars, not trillions. It requires decades of development, not centuries. The history of exoplanet discovery is instructive here, because it shows how rapidly the science of characterizing distant worlds has advanced without any spacecraft leaving the solar system. The first confirmed exoplanet orbiting a main sequence star, 51 Pegasi b, a gas giant in a 4-day orbit around its host star, was detected in 1995 by Michel Maire and Didier Queloz using the radial velocity technique, measuring the tiny Doppler wobble that the planet's gravity induces in the star's motion toward and away from Earth. The discovery earned Mayer and Quillos the Nobel Prize in Physics in 2019. But 1995 was only 30 years ago. In those 30 years, the exoplanet catalogue has grown from a handful of massive, close-orbiting hot Jupiters detected by radial velocity to more than 5,000 confirmed exoplanets, spanning a remarkable diversity of sizes, masses, orbital configurations, and host star types, detected by an expanding toolkit of methods: radial velocity, transit photometry, direct imaging, gravitational microlensing, astrometry. The transit technique, detecting the slight dimming of a star's light as a planet passes across its face, was transformed into the dominant exoplanet discovery method by the Kepler Space Telescope, launched in 2009 and decommissioned in 2018. Kepler monitored over 150,000 stars continuously for 4 years, measuring their brightness with unprecedented precision, and found over 2,600 confirmed exoplanets and thousands of additional candidates. The statistical analysis of Kepler's data revealed that planets are extraordinarily common. The average star in the Milky Way has at least one planet, and the number of rocky planets in the habitable zones of their host stars in the galaxy is estimated at billions. Billions. The raw count of potentially habitable worlds in our galaxy alone is in the billions, and the count in the observable universe is in the trillions. The TESS satellite, the Transiting Exoplanet Survey satellite, launched in 2018 as Kepler's successor, surveys the brightest and nearest stars, identifying the most accessible exoplanet targets for atmospheric characterization. By focusing on nearby stars, TESS finds planets whose host stars are bright enough to allow follow-up spectroscopic observations with large telescopes. The James Webb Space Telescope, with its unprecedented infrared sensitivity, is now able to characterize the atmospheres of some exoplanets by measuring the spectrum of starlight transmitted through the planet's atmosphere during a transit. For nearby systems around small red dwarf stars, where the planet-to-star size ratio is most favorable, JWST can detect the presence of water vapor, carbon dioxide, methane, and potentially other molecules in the atmospheres of rocky planets. The system receiving the most intense current scrutiny is TRAPPIST-1, a tiny red dwarf star, 39 light-years from Earth, that harbours 7 rocky planets, 7, in a single star system, of which 3 orbit in or near the habitable zone. The planets were discovered in 2016 and 2017 by the TRAPPIST telescope in Chile, and subsequently by Spitzer and JWST. They are roughly Earth-sized, tidally locked to their host star, and the innermost ones likely have surface temperatures incompatible with liquid water. But TRAPPIST-1 D, E and F sit in the habitable zone. JWST has already taken the spectra of TRAPPIST-1b and TRAPPIST-1c, the 2 innermost planets, too hot for life but useful as test cases, and found no evidence of substantial atmospheres, which is a concerning sign for the habitability of the system, though not conclusive for the outer habitable zone planets. At 39 light-years, TRAPPIST-1 is itself a destination that even the most optimistic interstellar propulsion concepts could not reach in any human lifetime. A probe travelling at 10% of the speed of light would take 390 years. At 20% of the speed of light, break through Starshot's target, 195 years. The TRAPPIST-1 system is scientifically compelling and physically inaccessible, and yet JWST is already reading its atmospheric signatures from 39 light-years away. The planets themselves are 39 light-years distant. The information about them is travelling to us at the speed of light, arriving every second, and we are learning to extract it. The search for extraterrestrial intelligence, SETI, adds another dimension to the question of reaching other stars. SETI has been an active scientific program since 1960, when the astronomer Frank Drake pointed the 85-foot Howard E. Tatel radio telescope at the National Radio Astronomy Observatory toward Tau Ceti and Epsilon Eridani, two of the nearest Sun-like stars, and listened for artificial radio signals. Drake heard nothing. But the program he initiated has grown over 60 years into a global enterprise involving multiple telescopes, a wide range of signal types, and increasingly sophisticated data analysis. The Breakthrough Listen initiative, funded by Yuri Milner with $100 million in 2015, the same Milner who funded Breakthrough Starshot, has conducted the most comprehensive SETI survey ever, using the Green Bank telescope and the Parkes radio telescope to observe thousands of nearby stars across a wide range of radio frequencies, and has found nothing clearly artificial. The absence of detected signals after 60 years of searching is itself information. It constrains the prevalence of civilizations that are actively broadcasting powerful radio signals detectable at stellar distances. It does not rule out the existence of such civilizations. We have surveyed only a tiny fraction of the galaxy with a limited range of signal types of a cosmically brief period. But it does place some bounds on how common powerful artificial radio beacons are in the galaxy. The Fermi paradox: if intelligence is common, why have we not detected any signals? That is a live question, and one that intersects directly with the question of reaching other stars, because the difficulty of interstellar travel is one of the proposed explanations for the silence. Perhaps civilizations do not broadcast because they do not travel, and they do not travel because the physics makes it too hard. Perhaps the great filter, the barrier that prevents technological civilizations from expanding beyond their home systems, is the same physics that we have been discussing throughout this video. The pragmatic answer to the question of whether we will ever reach another star, then, is nuanced. In the sense of physically sending a crewed spacecraft to orbit around another star, to land a human being on an exoplanet, probably not in the near term, possibly not ever without revolutionary new physics. In the sense of launching a robotic flyby probe to the nearest stellar system, possibly within a century or two, if civilization survives and prioritizes it. In the sense of characterizing the atmospheres of nearby exoplanets, detecting the chemical signatures of life if life is there, understanding what other stellar systems contain, certainly within the coming decades. Through the relentless advancement of telescope technology, without requiring any spacecraft to cross the interstellar void. This is the pragmatic answer to the question of whether we will ever reach another star. Perhaps not physically, in any near-term sense. But in the deeper sense, the sense that matters for science, for the quest to understand whether life exists elsewhere, for the profound human desire to know what is out there, we may reach the nearby stars within the current century. Via light and spectroscopy and a patient accumulation of photons in the focal planes of ever larger telescopes, we will read the chemistry of distant worlds. We will detect the signs of life, if life is there, in the spectra of their atmospheres. We will know what those worlds are, even if we cannot stand on them. The stars are 4 light years away. The light from them is already here. It arrives every second, carrying information about those distant suns and the worlds around them, and we collect it in the pupils of our eyes and the mirrors of our telescopes. We are already, in a sense, in contact with those stars. We are already receiving their transmissions. The question is whether we have instruments sensitive enough to read what those transmissions say. This is not a consolation prize. It is a genuine alternative pathway to knowledge, one that is, in certain respects, more powerful than physical travel. A telescope on Earth, characterizing the atmosphere of Proxima b, reads the chemistry of that world with light that has been traveling for 4 years. The light that carries the information left Proxima b 4 years ago. By the time it reaches Earth's telescopes, it has traveled 40 trillion kilometers and carried its message faithfully, unchanged, at the universal speed limit. The information travels faster than any spacecraft ever could, at the maximum speed permitted by physics, and arrives perfectly, without the degradation that any physical probe would suffer in transit. We are, in the deepest sense, already reaching the nearest stars. Every photon that left Proxima b 4 years ago and entered the mirror of a telescope on Earth last night was a direct contact with that stellar system. The stars speak to us in light, and we are learning to listen. This is the insight that reframes the entire question. Will we ever reach another star is not only a question about spacecraft. It is a question about contact, about knowing, about understanding what those other stellar systems are, what they contain, whether they harbour life. Physical travel is one way to achieve that contact, the most dramatic and most complete way. But it is not the only way, and it is not the fastest way, and it is not the way that is available to us on the timescales of current and near future human civilization. The way that is available to us is light. And we have been building better instruments to capture and read that light for 4 centuries. Since Galileo first pointed a telescope at the sky and found moons around Jupiter and mountains on the moon, and stars too dim for the naked eye scattered across the Milky Way. Every increase in telescope aperture, every improvement in detector sensitivity, every advance in coronagraph design that allows us to see dimmer objects mixed to brighter ones, every one of these is a step toward the stars. Not through space, through understanding. The two are not the same, but they are not entirely different either. To understand a thing fully is in some sense to have reached it. To know the chemistry of Proxima b's atmosphere, to have detected the presence or absence of oxygen and water and methane, to have answered the question of whether life arose there as it arose here, is a form of arrival. Not the same as standing on the surface, breathing the air, looking up at an alien sky where our own sun is just another point of light, but something real. Something that costs billions rather than trillions, decades rather than centuries, and does not require a civilization to survive 1,000 years of existential risk before it can be attempted. That reading, that careful, patient, scientifically rigorous reading of the light, is ongoing. It is accelerating. It is the great project of contemporary astronomy, carried out by thousands of scientists on dozens of telescopes on every continent and in every Earth orbit, building incrementally toward a picture of the nearby universe that is more detailed, more precise, more rich with information than anything any previous generation could have imagined. Whether we will ever physically travel to another star, step off a spacecraft onto the surface of a world orbiting a different sun, breathe air made by a different star's energy, look up at a sky where our own sun is just another star, remains genuinely uncertain. The obstacles are real and severe. The physics is uncompromising. The engineering is at the edge of what any realistic future civilization can achieve. The timescales are geological. Not because the universe forbids the journey, but because the universe charges a price so high that only a civilization far more capable than ours, and far more fortunate in its survival, can afford to pay it. But the universe is patient. It has been here for 13.8 billion years and shows no signs of going anywhere. The stars will still be there in 1,000 years, in 10,000, in a million. The question of whether we reach them physically is ultimately a question about what kind of civilization we become and over what time scale, and whether we survive long enough and grow ambitious enough and wise enough to do what the physics permits but does not require. The answer today is that we do not know. We might not. The obstacles are real and they are not easily overcome, but the desire, the ancient, persistent, ineradicable human desire to see what is over the horizon, to go where no one has gone, to know whether we are alone, is also real. And that desire, combined with the physics that permits the journey, even while making it hard, is perhaps the most human thing we have. It is the desire that sent boats across oceans before their navigators knew what was on the other side. It is the desire that pointed telescopes at the sky before anyone knew what stars were. It is the desire that sent a spacecraft called Voyager into the dark in 1977 and has been tracking it ever since, not because it will reach another star in any timescale that matters to us, but because the act of launching it, the act of committing to the journey and watching it go, told us something about who we are and who we want to be. The Voyager 1 is, as you watch this video, somewhere beyond the heliopoise, the boundary where the sun's solar wind gives way to the interstellar medium, where the sun's influence ends and the true interstellar void begins. It is the first human-made object to enter interstellar space. It carries a golden record, a physical artifact encoding sounds and images of Earth, greetings in dozens of human languages, the music of multiple cultures, photographs of our planet and its life and its people, on the chance that it might someday be found by another intelligence. It was launched in 1977 because Carl Sagan and his colleagues believed, or chose to act as if they believed, that the universe might be inhabited by minds capable of curiosity about other minds. The golden record is not a practical communication strategy. It is a gesture, a statement, a declaration that we are here, that we are curious, that we chose to reach outward rather than inward, that the stars matter to us even when they are unreachable. That gesture has been travelling through space for nearly 50 years. In 73,000 years, if Voyager were aimed at Proxima Centauri, and it is not, it would arrive. Not us, not a message, not a living being. A record of who we were in 1977, in a spacecraft that has been silent for 72,950 years by that point, assuming it continued to operate at all. By the time it arrived, our civilization would either be unimaginably transformed or no longer exist. The gesture would not be received in any meaningful sense. And yet, the act of making the gesture matters. It says, we tried. We sent something. We looked outward. We sent something called metal. We sent the times where we swear. We sent something. The obstacles are real. The journey will be, if it happens, the longest and hardest thing our species has ever attempted. But the light from those stars has been falling on our faces since before we were human. We have always been, in the most literal sense, staring at them. The question of whether we will ever reach them is not a question about the stars. It is a question about us, about whether we are the kind of thing that, given enough time, and enough wisdom and enough luck finds a way. And the answer to that question is still being written, one photon at a time, in the focal planes of telescopes aimed at the dark.